This is a video about springs and their extension, covering both the store of elastic potential energy in a spring and also Hooke's law. In this video, we'll define elastic and inelastic or plastic deformation, calculate the energy stored in a spring, calculate the force required to deform a spring, and have a quick look at the required practical that comes into this topic. We start by thinking about deformation, which means changing the shape of an object. In order to deform an object and change its shape, you need more than one force to be acting on the object. If there were just a single force, then the object would move. Deformed objects can be separated into those that are elastic and inelastic. Springs are elastic in nature. This means that when they're stretched by a force and then the force is removed, they return to their original length and size. This is different to materials that are inelastic, or we sometimes call them plastic, which can be permanently deformed and do not return to their original size and length when the force is removed. In reality, a spring isn't elastic forever. Every spring has something called a limit of proportionality, or we sometimes call it an elastic limit. And if you exert a force that is past that point, then it won't regain its original shape. You've probably seen this if you take a spring and you try and pull it too hard, eventually it just opens out until it's a curly piece of wire and it doesn't snap back. When they're squashed or stretched, springs can be used to store energy. When we do work on a spring by giving it energy, the energy is transferred into the elastic potential energy store of the spring. The amount of work done in joules equals the amount of elastic potential energy stored in joules. This is because energy is conserved, which means it can be transferred between different stores, but it can't be made or destroyed. This energy can later be transferred to other energy stores when the spring returns to its original length. If the spring has not reached the limit of proportionality, then we can calculate how much elastic potential energy is stored in it using the following formula. Elastic potential energy is half multiplied by the spring constant K multiplied by the extension squared. Extension isn't the total length, it's the change in length compared to when there was no force applied. We can calculate it by taking the final length of the spring and subtracting the initial length, the length before we did anything. The spring constant K is different for every spring and will usually be given to you in the question, unless they're trying to ask you to calculate it, in which case they'll give you energy and extension. Now, you don't need to memorise this equation because it comes from the second part of the GCSE Physics equation sheet, the part that you are given in the exam. But they will expect you to know what all of the letters stand for and what the units for them are. Let's practice using this equation to calculate elastic potential energy. Calculate the energy stored when a spring with a spring constant of 120 newtons per metre extends by 0.5 metres. I've been given the equation, so the first thing to do is to substitute in the numbers in the right places. 120 is the spring constant, so it goes where K would go, and 0.5 is the extension, so it goes where E would go. Now, looking at these numbers that I have, I need to think about my order of operations. I know from my BIDMAS rules that I'm always going to do an index before I do multiplying, so I'm going to square 0.5 before I multiply it by anything. That gives me half times 120 times 0.25. When I multiply all those numbers together, I get 15. And because this is a measure of energy, my units will be joules. We've said before that it's vital when doing calculations in physics to first check that all of your quantities are expressed in their standard international units. If they're not, then you may end up with an answer that's out by several orders of magnitude. But sometimes the exam board will give you questions containing measurements that aren't in their SI units, and so first we need to convert them. Here we've been given an extension in centimetres rather than metres. There are 100 centimetres in a metre, so before I can begin I need to divide that number by 100 to convert to metres. 7 centimetres is the same thing as 0.07 metres. Now I can substitute in the rest of my numbers. The energy stored will be half multiplied by the spring constant multiplied by 0.07 squared. Again, I'm going to tackle that squared term before I do any multiplying. That gives me half multiplied by 2100 multiplied by 0.0049. If I do that multiplication, I get 5.145, and then again, because we're talking about energy, this is going to be in joules. And remember, it's really important if you're writing shorthand to make sure it's a capital J. Now that we've done two examples together, here's one for you to have a go at on your own. Pause the video and calculate the amount of energy stored. So again, we've been given an extension in centimetres and we need to start by converting to metres. 40 divided by 100 is 0.4 metres. Now we can substitute in half multiplied by 4,800 multiplied by 0.4 squared. Tackle the squared term first, then multiply out, and your answer is 384 joules. We can also use a mathematical relationship called Hooke's law to make predictions about how much a spring will extend by when a force is applied, or to work out what force has been applied when we know how much it's extended by. This is how Newton meters and certain types of weighing scale work. Hooke's law says that the force applied to a spring is proportional to how much it extends by. Proportional means that if I double the force applied, the extension will also double. The equation that we need to take that general proportional relationship and turn it into numbers that we can use is this one. This is the third equation from the first part of the physics equation sheet, which means that you do need to memorise it. You need to know what F, K and E stand for and what their units are. So here we can say that the force applied is equal to the spring constant multiplied by the extension. Again, it's always extension, not length. We're interested in how much longer the spring has got. Straight away, let's start using this for some calculations. I want to know what force is required to extend a spring by 0.2 metres if it has a spring constant of 560 newtons per metre. The equation tells me that I just need to multiply the spring constant by the extension. 560 multiplied by 0.2 gives me a force of 112, and because it's a force, it needs to be expressed in newtons. Here's a trickier example. Calculate the force required to stretch a 20mm spring until it's 35mm long, given it has a spring constant of 1,920 newtons per metre. They haven't given me the extension in this question, so I need to work it out for myself. The final length subtracting the first length. 35 take 20 is an extension of 15mm. Now the other thing is that this extension is in millimetres, not in metres, so I need to convert it. There are 1,000 millimetres in a metre, so I need to divide by 1,000. 15 divided by 1,000 is 0.015 metres. Now I can use my equation. The force will be 1,920 multiplied by 0.015, which gives me a force of 28.8. And again, because it's a force, my units are newtons. Now here's one for you to have a go at. Pause the video and write down your calculation. Stretching the spring from 30mm until it's 60mm long is an extension of 30mm. Next, you should have converted that to metres by dividing by 1,000. Now we can plug that into the formula by multiplying it by 2,500 to get a final answer of 75 newtons. As with all of the physics equations, you need to be able to rearrange this one in order to calculate either the spring constant or extension instead of force. Here let's look at rearranging to make extension the subject. At the moment, extension is multiplied by spring constant. So in order to get it on its own and make it the subject of the equation, we're going to need to divide the right-hand side by spring constant. Whatever we do to the right-hand side of the equation, we have to do to the left as well. So we're dividing both sides by spring constant. Ke divided by k will be just e, and f divided by k will be f over k. So our final equation ends up looking like this. Extension can be calculated by taking the force and dividing it by the spring constant. Let's have a practice using that rearranged equation. Calculate the final length of a 25mm spring with a spring constant of 600 newtons per metre when an 18 Newton force is applied. So the first thing I need to do is to use my equation to work out what the extension will be. Force divided by the spring constant. So 18 newtons divided by 600 newtons per metre. That gives me an extension of 0.03 metres. But my original length wasn't in metres, it was in millimetres. So we're now going to convert back to millimetres by multiplying by 1,000. That gives me an extension of 30 millimetres. If my starting length was 25 and my extension is 30, my final length will be 55 millimetres. Here's one for you to have a go at. Pause the video and see if you can work out what the final length of the spring will be. Again, we started out by substituting numbers into the equation. 42 divided by 1200 gives me an extension of 0.035. Then I convert that to millimetres because that's the length that my spring is given in. 0.035 multiplied by 1,000 is 35 millimetres. Therefore, my final length will be 40, the starting length, plus that 35 extension, which gives me 75 millimetres. The mathematical relationship of Hooke's law will hold until the limit of proportionality is exceeded. This basically means that the spring will keep stretching in a proportional way until it hits that limit, and at that point it may stretch exponentially. You may have seen this happen while investigating the required practical around Hooke's law. In this required practical, you would have had a spring suspended, probably using a clamp stand and a clamp, and then you would have hung masses off it. You would have used a ruler to measure extension and probably used a Newton meter to calculate the force exerted by the masses you were adding. When you did the required practical, you may have displayed your data on a graph like this. But there's one thing about this graph that is quite unusual. In science, we always put our independent variable, the thing that we're changing, on the x-axis, and our dependent variable, the thing that we're measuring, on the y-axis. But when you did this practical, you almost certainly hung masses with a particular weight off the spring and then only afterwards measured the extension. So why have we flipped the axes in this graph? Well, there are two reasons. One is that it is possible to do this practical the other way around. You could stretch the spring until it's a certain length and then see what force is required to get that extension. But the other reason is actually a mathematical one. If we plot extension on the x-axis and force on the y-axis, then the gradient, dy by dx, is going to be the spring constant, and that makes that calculation much easier. From this graph, we can identify where the limit of proportionality is. As long as Hooke's law holds, extension and force are proportional to each other. That means that the graph has a continuous gradient, so we have a straight line. At the point at which the line stops being straight, we've passed the limit of proportionality. If you choose to plot your data with force on the x-axis and extension on the y-axis, then you need to be aware that rather than extending exponentially to the right, the graph will extend exponentially upwards when it reaches the limit of proportionality. This is mainly important if you're asked to draw a sketch graph in the exam. If they give you data, then it will be really obvious what to do. I hope you found that a useful introduction to all things springs in physics. Thank you very much for watching, and if you did find this useful, don't forget to like and subscribe for more GCSE Physics videos coming soon.